The James Webb Space Telescope, humanity's most sophisticated observatory for exploring the universe, has significantly expanded our cosmic knowledge. Its recent transmissions have astonished scientists by showcasing cosmic phenomena that question our current understanding of space. One of its recent highlights includes a revisit to the famous Pillars of Creation, an awe-inspiring formation located within the Eagle Nebula. First photographed by the Hubble telescope back in 1995, these giant pillars of gas and dust have never been seen so clearly. With the help of Webb's new infrared detectors, it has exposed baby stars forming within the pillars, some at close to a few 100,000 years old. This stunning find not only awes the eye but also enhances our understanding of stellar development and the dynamic processes at work creating such interstellar marvels. When scientists first laid eyes on Webb's images of the Pillars of Creation, the response was nearly universal wonder. Unlike Hubble's images in visible light, Webb's infrared perspective pierced the thick blankets of dust and exposed processes that had been hidden from humanity. What was once a mysterious cloud of shining columns is now a colorful vista of creation underway. The tiny, shining spots of light sprinkled about in the pillars are young stars, some of which are just a few 100,000 years old. To us, that may seem ancient, but in cosmic perspective, it's infancy. These infant suns are still enveloped in the remains of the clouds that gave birth to them, and Webb sensors enable us to see as they get ignited, grow, and start to shape their environments. Each pillar is like a cosmic womb, nurturing the next generation of stars that will one day sculpt their own galaxies. The ability to see these details with such resolution is not only breathtaking but also vital for astrophysics, since it helps answer one of the most important questions: how stars are born from dust and gas, and how these births affect their environments. After its success with the Pillars of Creation, the James Webb Telescope turned its attention to the Pandora cluster, named after the mythological figure who embodied inquisitiveness. Similar to the mythical opening of Pandora's box, Webb's observations uncovered breathtaking surprises. Using Einstein's general theory of relativity, Webb made a grand panoramic photo of Abell 2744, revealing about 50,000 infrared light sources, of which there are galaxies previously hidden from sight. These newly uncovered galaxies are thanks to the unique imaging abilities of Webb. The Pandora cluster, or Abell 2744, is a chaotic amalgamation of several galaxy clusters crashing into each other, merging, and distorting spacetime around them. The gravitational lensing of this vast mass warped the light of galaxies beyond, amplifying them as a natural cosmic telescope. Webb's sensitivity enables astronomers to observe galaxies as they were billions of years earlier, some of them within the first few 100 million years after the Big Bang. The size of the picture is difficult to grasp. Every glowing speck isn't a star but a whole galaxy, with billions of stars. The view takes in the cosmos's beauty and brutality, where galaxies smash into one another and pull each other into tidal streams, but also where secret galaxies from the beginning of the universe are uncovered in distorted light. Webb's journey did not stop there. It targeted a far-off stellar object called WR140, a unique type of star that is a Wolf-Rayet. The giant star is surrounded by concentric wave-like rings that are nearly artificial in their shape. What intrigued scientists was the slightly square shape of the rings, looking as though stopped in flight. Initially, most believed they had to be a product of Webb's instruments or an optical effect of light diffraction. But closer observation showed much more interestingly. WR140 is in a binary system, sharing a companion massive star. Each time the two stars approach one another in orbit, the strong stellar winds from each hit and crush gas and dust into shells that ripple outward into space. With time, these bursts of material pile up to create a sequence of rings, as if like the rings of a tree. The remarkable fact is that Webb captured them in exquisite detail, even with very faint squareness in their edges due to the physics of the colliding winds. This remarkable discovery not only proves Webb's precision but also raises new questions regarding the life cycles of stars, the creation of cosmic dust, and the bizarre symmetries that arise in the universe. One of the most shocking discoveries was when Webb picked up faint red galaxies at the outer limits of the observable universe. These giant galaxies, which are estimated to be 50 times more massive than others found so far, came into being when the universe was only 3% of its current age. Their existence contradicts current cosmological theories. Under present models, galaxies of that size should not have formed so soon after the Big Bang. The very existence of these giant galaxies suggests that either matter clumped together far faster than predicted, or that our understanding of early universe physics is incomplete. Scientists now aim to revisit these galaxies using Webb spectroscopic capabilities to study their light signatures, determine their composition, and uncover their star formation histories. The implications are profound, for they could reshape our understanding of the universe's formative years. If giant galaxies did exist so long ago, then galaxy evolution models will need to be rewritten, and the aftermath of the Big Bang might have been more energetic than we ever knew. With its advanced infrared capabilities, the James Webb Telescope can reach through thick cosmic clouds and dust to reveal areas where stars are currently forming. These star nurseries, long invisible to other telescopes, provide astronomers with infrequent windows into the earliest phases of star formation. Some of these finds include a compact cluster in the Tarantula Nebula, within an area known as 30 Doradus. Webb revealed hundreds of protostars and young stars at different stages of development, allowing scientists almost real-time insight into how stars form and develop. The Tarantula Nebula is among the most vigorous star-forming areas of its kind, and with Webb's eye, its intricacy is unveiled. Gas, dust, and radiation play a dance that produces giant cavities where material is pushed aside by winds from infant stars, while in other places knots of gas are so dense they collapse to create the next solar generation. To astronomers, these pictures are a laboratory where they can try out hypotheses about how stars light up, how star clusters are born, and how big stars shape the galaxies that surround them. Webb's state-of-the-art tools aren't reserved for distant galaxies. They're also revealing secrets of planets outside our solar system. By measuring light that passes through the atmospheres of exoplanets, Webb can see specific chemical signatures that tell their composition. Perhaps the most thrilling discovery is detecting water vapor in the air of distant gas giant exoplanet WASP 96b. Finding water is a milestone, not because WASP 96b itself is habitable, it's much too hot for life, but because it demonstrates that Webb is capable of detecting life-critical molecules in hostile extraterrestrial skies. This significant advance brings us closer to identifying potentially life-supporting planets. In the coming years, Webb will shift its focus to rocky planets within habitable zones, the so-called Earth-like planets where liquid water could exist on the surface. If Webb finds biosignatures, chemical signatures like oxygen, methane, or ozone, it could be the first sign of life beyond Earth. For the time being, the WASP 96b finding is an exciting proof of what can be done, paving the way for arguably the most monumental find in human history, proof that we are not alone. The James Webb Telescope has also shed light on one of the universe's most mysterious mysteries, dark matter. Invisible stuff that neither emits nor absorbs light, dark matter constitutes approximately 27% of the universe. Its presence is understood only from its influence on gravity, but its real nature is one of science's biggest enigmas. Through the study of gravitational lensing, in which great cosmic clusters warp light from objects behind them, Webb has assisted in the construction of precise maps of dark matter distribution. Its enhanced sensitivity to detect the lensing effects enables scientists to better estimate the mass and dynamics of these unseen components. These observations provide crucial clues to the scaffolding of the universe, the hidden web of dark matter that shaped the distribution of galaxies and cosmic structures after the Big Bang. Each step forward with Webb brings us closer to demystifying dark matter, though the ultimate answer still lies beyond our grasp. Another major advancement from Webb's research lies in measuring the universe's rate of expansion. By examining redshift, the stretching of light due to the cosmic growth of distant galaxies, Webb has achieved unmatched precision in calculating the speed at which the cosmos is expanding. However, its findings have added complexity. There appears to be a mismatch between the universe's expansion rate in its early history, as measured by the cosmic microwave background, and the rate measured today using nearby supernovae and galaxies. This difference is referred to as the Hubble tension, and data from Webb only refined the issue. The disparity suggests unknown forces or novel physics at work in cosmological acceleration. Is it a new type of dark energy, or a defect in our gravity models? These are fundamental questions to the discipline of cosmology, and they pose profound questions concerning the ultimate fate of the universe. Will it just keep growing forever out into an empty, cold space, or might some unknown processes come to slow or even reverse its expansion? One of Webb's main jobs is to find the first light sources, galaxies and stars, that formed in the universe's first couple 100 million years. These early buildings are crucial to knowing how the universe was formed. Webb has already peered at some of the most remote and faint galaxies ever observed, their light traveling over 13 billion years to reach us. To look at them is like gazing through a time machine, back in an age when the universe was still veiled in hydrogen gas. These observations assist researchers in reconstructing the initial stages of the universe, revealing how matter coalesced into stars and galaxies following the Big Bang. For the first time, astronomers are able to witness how the cosmos evolved from darkness to light during what is referred to as the era of reionization. Webb's findings here are perhaps its most significant because they map out the initial glows of cosmic dawn. Whereas Webb is great at revealing how stars are born, it has also provided fantastic insights into how they die. When huge stars burn through their fuel, they explode as supernovae and scatter heavy elements into space. Webb's ability to image these disastrous happenings in incredible detail has enabled astronomers to investigate stellar life cycles more profoundly than ever before. Among the vibrant wreckage of such explosions are elements like carbon, oxygen, and iron, also the same ingredients that constitute planets, oceans, and even us. Life is sown through these stellar deaths. Webb has seen this reusing of material throughout space and unveiled the basic processes that tie stars to planets and planets to life. All the iron atoms in our blood once existed within a star, and Webb's observations remind us of this deep history. Webb has also studied quasars, incredibly bright objects fueled by supermassive black holes devouring colossal amounts of material. Targeting some of the most distant quasars on record, Webb provides new information about these mysterious sources of power. These quasars, born when the universe was young, outshine whole galaxies. They tell us important things about how the earliest black holes were born, how they grew to such colossal size, and how they influenced the galaxies that surrounded them. Data from Webb indicates that black holes and galaxies co-evolved, each shaping the other in ways that ripple through cosmic time. Unraveling quasars is the first step towards understanding how the early universe developed into the rich structure that we observe today. Aside from discovering densely packed galaxies, the James Webb Telescope has unveiled the emptiest parts of the universe, cosmic voids. These vast lightless areas, extending hundreds of millions of light years, pose yet another enigma. Why are these regions so matter-poor, and what is responsible for their creation? By observing the edges of those voids and the galaxies that line them, Webb is assisting scientists to construct a fuller image of how matter is dispersed across space. The identification of these voids contributes to the fabric of cosmic structure, reminding us that the universe is not filled uniformly, but rather a galaxy web of emptiness, of clusters and deserts, of chaos and order entwined. With all these advances, the James Webb Space Telescope not only rewritten our knowledge of the universe, but has also revolutionized the way we understand our own position within it. From witnessing star birth and demise to picking up on ancient galaxies and studying dark matter, its discoveries have revealed a more complex and majestic universe than ever conceived. Every picture taken by Webb is more than a photographic record. It's a journey through history, a peek at the birth of all we understand. With every discovery, there are more questions. What forces shape galaxy building at the edge of the beginning? Might the unknown territories of cosmic vacuums hold secrets to the fate of the universe? And what do the discovery of distant Earth-like worlds portend for the possibility of life beyond Earth? The James Webb Space Telescope is not only a science instrument, she is a storyteller of the cosmos, opening pages of a galactic story that humanity has only just started reading.